Hello, everyone. So now we will be looking at a Python code demo, which will show us how LDA performs in practice. So like before, we will be using Google Colab to run our code. So you do not need to install any additional tools. You will need to first run this cell with the import statements, which should run out of the box. And we are just going to use NumPy and a little bit of matplotlib for plotting and sklearn. So our code consists of two major classes. The first one is the dataset class. We will go through the functions of the class one by one later. But for now, the overall picture is you have this one dataset class, and in the next cell, you have this one class which codes the LDA classifier. And now in the cell after that, we have a block of code which uses the above two classes and runs it. So we will, in order to have a walkthrough of the code, we will start with this original trigger set of lines, and then we will dive deeper into each of the class functions one by one. So for today, we are using the MNIST digit classification dataset. And some of you may have noticed that we import TensorFlow in the first cell. And the primary reason for that is that it allows for a very convenient way of downloading MNIST. And I don't think we are going to use it anywhere else. So once you are fetching the MNIST dataset, you have the load data function, which already has this split of train and test. So you directly initialize the features into the xtrain and the xtest respectively, and the labels in the ytrain and ytest respectively. Okay. So if you remember, the MNIST classification is an image classification dataset, which has individual pixel values between 0 and 255. So here we are just normalizing the numbers, the features between 0 and 1. Right. So here is where the first class is being called. So remember, this is the dataset class, and that is being provided the input training data, including both the features and the labels. So let us look at what this line of code does. So I'm going to scroll up now. So here is the dataset class, and that line of code would have called the initialization module, which is the init function. And we had the training data features X and the targets Y. And this was not explicitly passed to the function, so this remains as the default none. And as you can see, if the valid class parameter is none, then it simply looks up the number of unique classes in the Y input. So it's checking the number of unique classes in the targets, and it's initializing that valid classes variable, which then gives it the number of classes in the dataset. That's all there is. The second thing the initialize function does is to call this toDict function on top of both the X and the Y inputs. The toDict function basically loops over the entire input dataset, which was our training data, and then it checks in which class each of the data item is belonging to, and it creates a dictionary on that data. So the dictionary is indexed by the class IDs. So the keys are the class IDs, and for each class ID, it is storing the corresponding data features in a list. And you will also notice that the data features are flattened. So remember, the MNIST data is an image classification dataset, which means that the features are in form of a square matrix. In particular, it is in form of a 28 cross 28 square matrix because it's an image of that size. And this is simply flattening it into a one-dimensional row feature vector. So 28 times 28 is 784. So each of the data item is now visualized as a 784 dimensional row feature vector. So this is the flatten function. And then for every class Y, it is simply appending, or it's concatenating all the input data items for that class. So this allows for an easy lookup. So suppose you want to fetch all the data items which belong to class 0, you will just look up in the dictionary and the set of data items will be returned to you. And this is useful because remember in LDA, we operate on one class of data at a time for various computations. Right. So this is just a NumPy conversion of the input data and it's returning the data dictionary. So this is the initialization module of the dataset class. So let us go back to the part of the code that was triggering this. Scrolling back down, we are back at this line of code. So here the initialization of the data dictionary and everything has happened. And now you see on top of this initialized object trained dataset, it's calling the get all data function, which is returning some values. So we will now look at the get all data function. What does it do? So I'm going to scroll back up again. So here is the get all data function. So what this is doing is that it is looping over all the data items. So remember, data was the dictionary that was created here. So if you remember, in the toDict function in the initialization module, it had created this dictionary and it was storing it in this self.data object. So it is simply referring to the same self.data object and it is looping over all the items and it is concatenating all the data and the data features and the labels in a single NumPy array and returning it. So there is no class-based division here that was there in the dictionary. It's just appending all the data items in one single list and then returning it. So that's the get all data function. And also you will see there is a get data by class, which is just using the dictionary to quickly fetch all the data items which belong to a certain class. The class ID is given as an input here. So this more or less covers all the functions that are part of the dataset class. So now let's go back down to the part of the code that was again triggering everything. So we have covered these two lines of code, the train dataset and the get all data function. And it has also printed the data statistics. So you will see we have 60,000 data points. And as promised before, you have 784 features per data point. And of course, the label is just a 60,000 length single vector because it's just one integer denoting the class ID. So now we are using the sklearn function called LDA classifier. Okay, so the classifier this is the function that we have written for LDA classification. So we will again discuss this one by one. It uses sklearn somewhere in there, but most of the code is written by us. One input to this LDA classifier is the number of dimensions that you want to project the data to. So remember, this is a multi-class classification target. So the number of classes are, I think, 10 because there are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 distinct digits. Here we are asking the classifier to project down the data to 2 dimensions. So let us now look at the LDA classifier object and see what this does. So scrolling back up, if you look at the LDA classifier initialization module, it's first taking the projection dimension and storing it in the self.projection dimension object. And then it's initializing a bunch of different values. All of these are initialized to none. We will see how each of these are being used later. So not much is happening in the initialization module of LDA classifier. So scrolling back down to the code that triggers it all, the initialization part is done. And now the fit function, which is defined in the class, is being called. The input to the fit function is the dictionary version of the data. So the dictionary that had the class specific list of data items that is being provided as an input to the fit function. So let us see what LDA classifier fit does with that input. So going back up to the start of the fit function, first of all, you see that it calls this compute means API, which is defined below. So what does the compute means do? So here is the compute means function. It's taking as input the feature matrix X. This X is the same one that we have been seeing everywhere during the lectures. And then for every item in the data dictionary, it's just taking the mean of the items in the class. So it's a very simple operation. You remember the dictionary gives you the per class list of data features, and it's just taking the average of the data points belonging to the class. And it's returning a dictionary of the means. So now, after the per class averages or the means have been computed, it's computing the intra-class variance for each class, right? So the scatter matrix which encodes the intra-class variance. So for that, once again, we are taking the features for the data items in each class. We are subtracting the mean of that specific class, and then we are doing the outer product. So these are the individual scatter matrices for each of the class. And like you have seen before, we need to add up those scatter matrices to get the SW term which is there in the denominator. So this you should be familiar with. This is a D cross D matrix which encodes the intra-class scatter. So the denominator of our objective function is computed. What about the numerator? So that's next. So here it's doing nothing, but it is looping over all the data items, right? And it is finding the number of points in each class. So data.shape0 gives you the number of data items in each class, and it's just creating a dictionary NK for the count of data items in each class. And then it is also adding up the total number of data items in the entire training data set across all classes. So that's the sum of the data items, right? And given the total count, you can use this sum of the data for all the training data sets, and you can divide it by n to get the overall data mean. So you have two things till now. You have the mean of the entire data set that you need, and you also have the class specific means, right? So given that, you can now use the formula that we have seen before to subtract the class specific means from and the overall mean, overall mean of the total data set, and then you can compute the outer product. So this formula should be familiar to you. We are multiplying NK times the outer product of the class means. So this basically gives you the interclass or the between class covariance matrix that we need for the numerator, right? All right. So now what this code does is to use the eigenvalue solution to find the W's. So for that, you remember we had to compute the eigenvalues for SW inverse times SB. And this is just computing that matrix. And then in line 40, we are using the inbuilt EIG function to compute the eigenvalues and the eigenvectors of that SW inverse SB matrix. So now remember that the step after this eigenvalue decomposition is to find the eigenvectors corresponding to the topmost eigenvalues. So since here we are requesting the LDA class to fetch us the top two projections, remember the projection dimension is 2. Therefore, we want the eigenvectors which correspond to the highest two eigenvalues. So for that, what do we need to do? We need to first take all the eigenvalues and then sort them in reverse direction. So it's creating a list of those eigenvalues in this line. And then in this line, it's sorting it in reverse direction. And then it is taking the top two, projection dimension is 2 here. So it's taking the top two eigenvalues and then fetching their corresponding eigenvectors in this line. So this is the W that we need. And this is basically the output of our LDA classifier. And also remember that our next question is how do we actually use these Ws for prediction? So you have projected, once you project the data into a lower dimension using these Ws, there are two Ws here. How would you actually use it for your classification task? And for that, we were discussing something about learning a Gaussian prior, and that is what is being initialized in this line of code. So if you look at this Gaussian function, which is initializing some prior values, it's setting some parameters basically, then what it is doing is, it is looping over all the classes and the corresponding items in the class. It is projecting the, for example, corresponding to this class ID, it's taking all the data features and projecting it into the lower dimensional space by multiplying the feature matrix with W. And then it is computing the projected mean and the projected covariance, right? And that is, giving us the mean and the variance for the Gaussian distribution for that projected data points in the class. Also, the Gaussian requires a prior, which is nothing but the fraction of data items which belong to that specific class. So that prior is being computed here. It's dividing the number of data points in that specific class by the total number of data points, and that's just a prior. And it's returning the mean, the covariance, and the prior values. So this is initializing all the information that we need to learn our Gaussian function-based discriminator. So this brings us to an end to what is happening in the init function, in the fit function of LDA classifier. All right. So going back to the code which is triggering it all, remember for the LDA classifier, we were initializing it and then we were calling the fit function. And then finally, what's happening is we are calling the score function. So what does this do? Let's look at it once. So this score function is taking as input your X and Y. The first step is to project your X to the whatever lower dimension there is. For that, it's calling this project function. The project function, as you can see here, is nothing but a dot product between the input features and the Ws. So once you have projected down the features to a lower dimension, then for all the items in the projected space, it is simply computing the posterior probability of that data point belonging into this class, into each class. So for all data points in the input to the scoring function, it's first projecting it into a lower dimension. And then for each class, it is computing the posterior. How do you compute the posterior? There is a formula which uses the prior and then the Gaussian distribution values using the parameters that you had learned earlier, the mean and the covariance, and that gives you the posterior of that data point belonging to the class. Okay. And then it is just storing the probabilities of each data point belonging in the C classes in this row, right? So this is basically the Gaussian likelihood of that data point belonging to each of the C classes, right? And your final prediction is basically the argmax of the Gaussian likelihoods. So let's say there are 10 classes and you have a likelihood for your input data point belonging to each of those 10 classes. You will predict that the data point will belong to the class which has the highest likelihood. So maximum likelihood estimation. So this is basically checking the argmax or the maximum likelihood estimate of the data input items given the Gaussian posteriors, right? So this is the scoring function, which is returning the predictions. And going back to the clf.score, it's giving the input and the targets. This input targets are the consist of all the training input and targets. This is not the dictionary version. This is the total version of the input. And it's scoring it and returning an accuracy value. So you will see in the scoring function that it's adding up all the prediction. It's adding up all the cases where the predictions match the label and then dividing by the total number of items. And that gives you the accuracy. So it is computing the accuracy. And what this tells us is that the training accuracy is 0.576, so 57.6% when you have the data set being projected down into a two-dimensional space. So now let us look at some visualizations. So here we are visualizing how the projected data set looks like in the 2D space that we have done in the previous setup. So I'm zooming out, so the text will not perhaps be that visible, but the image should be quite clear to you. So here you see that you have these classes which are color coded in different colors, basically. And as we can see, the classes are quite separable. It's not that bad. You can see some linear boundaries between them. However, there are some classes which are split into multiple segments, right? So this projection into two dimension is not being able to ensure complete linear separability of the classes. So that's why the accuracy is also a bit less. It's 56 point something or something like that, 57%, right? So what happens if we increase the number of projections? That's a question that we will answer in a bit. And the other visualization that I hope is visible to you, so I need to zoom in a bit more, is what the Gaussian distribution looks like when it's classifying the points during inference. So as you can see, this is the three-dimensional version of that 2D plot that we saw just before this. And each of the Gaussian distributions are visualized by using the mean and the variance function that we, mean and the variance values that we computed earlier. And this is the Gaussian distributions that our LDA classifier model is using to classify the data points during inference, right? This is just a cool visualization. So zooming back out so that the code is now a bit more visible. Here, what we are now checking is what happens if my projection dimension is increased. So it's again creating another instance of the LDA classifier. Now it's asking it to project the data points down to a three-dimensional space. And then it is fitting the LDA classifier on the training dataset like before. Also, it is using the test dataset for predicting the accuracy. And here you can see that the accuracy increases to 74.2%. So just by increasing the projection dimension from 2 to 3, we have a boost in accuracy from 56% to 74.2%. So just to clarify, I also want to point out that in this previous example, where our test accuracy was 56.5%, this was slightly lesser than the training accuracy. However, while evaluating our ML models, we do not care for the training accuracy that much. We only care about the test accuracy. And so this is a point that we should keep in mind. So now you can see clearly that increasing the projection dimension to 3 increases the test accuracy from to 74.2%. Now the question, so here also, since we are projecting it down into a 3D space, there is some visualization possible. So as you can see here, this is the visualization of the 3D space into which we have projected the data points. It's not quite clear because here the purple points are hiding behind the yellow points, but there seems to be a better separation between the classes because the accuracy has improved drastically. Unfortunately, visualization beyond 3 dimensionals will not be possible. However, as part of the assignment, I encourage you to explore what happens if you increase the number of projection dimensions, right? So as we have discussed just a little while back, you can ask LDA to project the dimensions up to C-1 classes, where C is the number of C-1 dimensions, where C is the number of classes. So does the accuracy actually improve if you do that? So that is one task that you can check using this code that we will provide to you. Secondly, if you plot the accuracy versus the dimension of the projection, does increase the dimensionality beyond C-1 give any benefit? So it should not, ideally. Mathematically speaking, it should not. But I encourage you to explore and try out whether increasing the dimension beyond C-1 is of any help. The third part of the assignment can be something like this. So like I said before, this is the MNIST digit classification dataset. So you can take a subset of the dataset which only contains data for digits 0 and 1. So now this is no longer a multi-class classification dataset. It would be a binary classification dataset involving 0 and 1. So remember that we had discussed an easier solution for the LDA objective in the last lecture, which did not involve computing the eigenvalue and the eigenvectors, right? We only had that SW inverse times M1 minus M0 to get the optimal W. So it will be interesting to confirm that the W that is suggested, that is given by that easier method, whether or not it matches the W that you would get by using eigenvalue decomposition. So I encourage you to try this, and in case you run into any problems, please do get in touch with us and we will be happy to help. Thank you.